now to the classroom mode, and we'll study the topic of cross validation. Good.
In the regression classing, you can use the same feature twice, right? Like
Yes. Okay, so previously in the lecture we had discussed the bias variance trade-off, and we looked at it from two angles. Can someone quickly remind those two angles? The first is called underfitting and overfitting. What do you mean by underfitting and overfitting? Okay, the fourth row. 1, 2, 3, 4, fourth row. Sorry? Bias is underfitting, yes. What do you understand by bias and underfitting? So I just want all of you to remember a few lines. Underfitting is, remember underfitting, you are not able to fit well on the training data itself, which is very likely to mean that you will not be able to do well on the test or generalization data, which means your model is typically very weak, which also means that you have perhaps made very biased, wrong assumptions about the complexity. You have assumed the complexity of the underlying data to be quite simple. So bias, underfitting are looked at it in this way. The other perspective of bias is that because you are not able to fit well, the true function and your fitted function show a lot of bias or a lot of differences. On the other hand, we looked at variance. On the other hand, we looked at variance, which is the zone where the model has learned. So the x-axis is the complexity. The model has fitted very well on the training data set, but on the test data set it starts showing diminishing returns, or not diminishing returns, sorry, it gives a bad performance. This happens because your model, because of the high flexibility or the tuning knobs it has, it tunes to the very specifics of the training data set and it misses out on the larger piece, which is the generalization. No, this one. So where we had seen the other interpretation of overfitting is also variance, high variance, because a small perturbation in the training data will lead to a very different model being learned. Right? Because it has a lot of tuning knobs, that's why you will be able to learn a very different model. Any questions on the bias variance trade-off? So it's one of those topics where you'll get a lot of questions in your interviews also, and that's where a lot of students have made mistakes also. So a relatively simple topic, but also it has some chances of making mistakes. Okay, so today we'll be talking about cross validation. In the general machine learning pipeline, we have discussed this workflow as of now. We are given some training data set, we train a model on that, our model is learnt, which we then use to predict on a test data set. We call the test data set to be unseen. Unseen till the point we have trained a model. Once we have trained the model, so we then use the input features from the test data set and our model to make a prediction. We get the predicted labels. In the case of regression, continuous values. In the case of classification, discrete values. But the test data set also has the actual labels. So we can then compute the metric between the actual labels and the predicted labels and compute the accuracy or error, etc. So one common confusion which I have seen at this place, this stage is, and I'm surprised I didn't get this question. You said that, so I said that the test the test is unseen, right? How do I get the labels for that? Right. So we'll have to consider two scenarios for this. The first, where we're doing this in a lab-like setup or in a simulation setup, where let's say I had 1,000 rows of data, I will use some part of that for training and some part of that for testing. Whereas in the actual deployment stage of things, we will never have the true labels. Let's say if Amazon or Google or any of them have deployed their models for, let's say, recommendation engine or for the price of forecast or whatever quantity of interest, they will never know the true labels until and after the event has occurred in certain cases. Right? In cases of whether if you're doing weather forecasting, the true labels would be made available, but they'll be made available after you've made the forecast and 1 day later, let's say. So typically weather forecast like systems, you have to give a k day ahead prediction. So for today, given today's date, I have to make a prediction for tomorrow, day after, so on and so forth. Is the true weather information for tomorrow and day after available to me? No. But that's why these things are typically studied retrospectively, where I would have seen, I would let's say go 3 days ahead in the future. I'll see what prediction I made, and by that time I would have already got the ground truth. But that's a simulation setup. But when actual decisions have to be taken, it's not in a simulation setup, it's in a real world setup, where the ground truth label are not available.
So how is this different from the argument, as in the flow that I'm saying right now? If you just consider the case of weather forecasting, I consider data from Monday to Wednesday as my training set, the data on Thursday as my test set. Now my model has been developed, it has been tested that it is working or not, and then for Friday, Saturday, Sunday, I will predict it and then verify.
Yeah.
So predict it, so it's working. So why not do verification on a part of test data set only, like the known data set only?
So that's exactly what we do. We always, so this is the primary reason why we split our data, our known data where we have the labels, into training and testing, because we need to tell how good our model is, right? So let's imagine that tomorrow I come up with a very, very sophisticated model, and I'll tell you that I can't tell you the metrics because the test set is unknown to me. Is that a fair thing to say? No. So for all of the fields you'll see in engineering, you would have seen that there are commonly known benchmarks. Benchmarks are a specific set of tasks, very well specified set of tasks, where you know how much performance measure is the state of the art and how much you can beat. For those reasons, we typically have a full data set with labels, a part of which we reserve for training, a part of which we reserve for testing. So that is on the creator of the algorithm to ensure that, or of the implementer, to ensure that the train and test set are kept separate. Sometimes people, I've seen students come to me and they say that they've got 100% accuracy. You should be very careful when you get such high numbers. It typically means that there is some leakage between the training and the testing data. Right? So one of the reasons why this happens is during the training process, you've already seen the test data. And then you test the performance on the test data and you say that I get 100% accuracy. What is a problem that you envision with this machine learning workflow?
If we later find out as per new data that a model is not very accurate, we cannot change it.
Okay, so Deep says that if we later find out that the model is not very accurate, then we can't do much. So this is a specific problem known as distribution shift, when your models have to be retuned because of certain shifts which have happened. Right? So an example of this might be, let's say we had a machine learning model to predict the energy consumption of the campus. It was working perfectly. The mean squared error was very low, but then COVID happened. What will happen to a model? It will perform very poorly. So a reminder again, please, no laptop policy. Please, can you turn off your laptops? It's disturbing to the others. So during COVID, the model will have to be, in certain situations when interventions have occurred, interruptions have occurred, the model will need to be redeployed. But this is actually a simpler question which I'm asking. So just look at this slide and tell me, do you see any shortcomings in this workflow?
We can't understand how well the model has trained during the training process.
We cannot understand, okay. So I'll just rephrase what Jaydev has said, that we have trained the model based on certain assumptions. For example, for our case, the assumptions were that we'll use a decision tree of a certain depth. Right? So these things are typically known as hyperparameters, like the depth of the tree or the information gain criteria that you use, whether it's Gini index or whether it's information gain / mutual information. So these are things, hyperparameters are things which you use in your algorithms, but they are set before you do any training, right? So hyperparameters are things like the maximum depth of the tree you want, but these things you don't learn from the training data set, you have to pre-specify them. So his argument is that we cannot choose a best depth. So maybe the best tree, the most accurate tree turns out to be of depth 5, whereas the default one is of depth 100, right? So there is no way in this current setup that you're seeing on the screen to determine what the optimal depth of a tree should be, or what the optimal hyperparameter should be. That's one important flaw of this train test paradigm. What could be any other problem? The split between train and test may cause what problem? It might be biased. So how might it be biased? Can anyone give me an answer for that? So one says that maybe when we are trying to do a classification between dogs and cats, during the training part we have only seen dogs, during the testing we only have cats. Right? But we are not very naive or stupid to make such mistakes. That's what we'll typically think, right? But whenever we do any regression like setting, actually let me write some code and show you how that kind of a mistake might come. Okay, look at this code. I want to do a 50-50 split of training and testing. Right? I have created my data, numpy.linspace, linearly spaced data between 0 and 100 points, and my true function is sin of x, my y values is some fx plus some epsilon noise, and I do my split as first 50 values go in training, the remaining 50 values going in testing. Is this correct or wrong? What is the problem in this code? No, everything is in front of you. We know the data's distribution exactly.
It's like we know if the first 50 values are, let's say, considering just 0 to pi range, then pi to 2 pi range, this other division we don't know about. So
Yeah. Can you see the specific bias which exists in the training and testing? Your training test train split has only seen the first 50 sequence of points. The testing set has only seen the remaining 50 sequence of points. In this case, it may not make a lot of difference, but maybe I had a function which was also defined in a way which is a specific function the first 50 points, another function for the next 50 points. So these are good experiments you can actually do to check. Okay, what do I need to do in order to make this better, to remove the bias? Randomly do what? Randomly split? How do you randomly split? Shuffle the data, right? So you can do something like numpy.random.choice of from 100 numbers you want to choose 100 numbers with replace equal to false, and you guessed a list of numbers, right? So you pick the first 50 of these are the indices, right? You pick them as your training set, the last 50 as your test set. Right? That way you have removed the bias which existed in the sequential nature of the data.
Also, so is always training and test data distributed 50, or it can be?
So typically you don't do it 50-50, typically 70-30, 60-40, 80-20 kind of things are used. The important thing is that whatever you choose, the split you choose, you use it uniformly, exact all of the algorithms.
But sorry, another question. But if our training data set is, let's say, 90-10 and or 80-20, 90-10 will be, might give us a better model as compared to 80-20
Okay.
because it is getting more information to learn.
Okay, so Deep's question, and let's try and answer this question. He says that a 90-10 split may be giving you a better model because you've seen more data. What do you think about this argument? It may also overfit, it may also not have, because you only have 10 points in testing, maybe you're not able to test enough points. So you can't generalize the performance well enough given a small test size. So therefore you need a delicate balance between these. But the most important thing you have to do is to choose the train test split before you do the study, and after you've done the study, then during the study compare all the algorithms. So never make this cardinal mistake. I've seen some people make this mistake. They choose the train test split which gives them the overall best accuracy. Never ever do that, right? So what they'll think is that let me choose whether I should do 60-40. If I use 60-40, I get 80% performance. If I do 70-30, I get 90% performance. So let me use 70-30. What you're not realizing is that the baseline algorithms or the models, the algorithms that you're trying to beat, they would have also similarly benefited from this slightly different split. So never go down that rabbit hole of choosing a better split in order to get you maximum performance. I've unfortunately seen this happen a lot of times, so let's avoid this.
Could you repeat the reason for not doing this?
So you always, so it may be something very specific to the data that you have used which creates some changes in the numbers. You should always, so and the next thing which we'll see, the next slide, is a countermeasure to this. So let me first come to that. We've seen that it is not utilizing the full data set for training and not for testing also, right? So perhaps even though after random shuffling you've taken your due measures, but it's still possible that there were certain test points which were slightly harder to get, but they're not in your current test set. So in which case you'll not be able to say that your model is generalizing well because you've not tested your performance on each and every test point. Second, there is no way to optimize the hyperparameters in this setup. Let's try and solve these problems one at a time. Before that, I can quickly show you some code on how to do this. So this code can get a bit overwhelming because this is involving quite a few things. Don't get too bogged down by the specifics of the code. As long as you broadly understand the slides, the specifics of the code you can work out at your own time. I am doing a fixed 70-30 split. I am using a function from sklearn called train test split. Test side is 30, so 30% of the samples are used for testing, and my random state is 0. So you should always, when you're doing a train test split, always specify the random seed to have reproducible results. So I have plotted the overall data. What I have not shown, which is also a good practice to show, is to also plot the train and the test set. And then you can see, you should see that if there are certain biases which exist, and then you can eliminate those. Because I cannot tune the hyperparameters, I will use the default hyperparameters. I will train on my train set, I will predict on my test set, I will get some accuracy numbers, which is 88.33%. Now, I've said that this has one problem. It has not tested on all the data points in the data set. It has only looked at a small set of them. How do we counteract that? And don't tell me k-fold. Tell me something in between. So, if chosen one specific 70-30 split, what could you do to ensure that each and every test point has been seen? Like you have tested on each and every test point.
Why not take the training set and test set, like take the entire superset and take same proportion but with different random?
Multiple times, right? So this is with one random seed, you acquired certain 70-30 split. With another random seed, you will acquire a different 70-30 split. Can you do that? So it's a simple technique, but that is also in some ways stochastic in nature. So you're not guaranteed that each and every point would be a part of the test set at least once. You're not guaranteed that, although probabilistically very likely to happen, but not guaranteed. and you'll have to run the experiments a large number of times to ensure that. Right? It's wasteful. Is there a question? So in this case, you see that I've done the split using random state equal to 0. This gives me a certain 70 points for training, certain 30 points for testing. If I change the random seed, I'll get a different 70-30 split. If I keep doing that over multiple times, it's very likely, it's very probable that I would have tested each and every point as a test point. But it's very computationally expensive to do this. So if we did multiple random splits, I am doing 20 random splits with a different random seed in each. I am doing everything else as the same in the previous case. I look at the mean accuracy across the 20 random train test splits, and I then report the standard deviation. I look at the min and the max accuracy. So you have to compute all of these terms and show. What is typically done in practice is, okay, so I said that we can use different parts of the data set. The challenge is it may not use every data point guaranteed, and it may be computationally expensive.
So my question is, now that we have used the testing training data set, it might happen that the depth of the tree is not, the tree is not, has not got enough depth, so even the generalization is not proper. So should we also not train on a subset of test data, training data set, and verify that is our depth enough or not?
Yes, so Deep's question we'll answer in the next slide. That's exactly what we do. But a simpler method to utilize the entire data set is known as k-fold cross validation. Right? So it's actually just k-fold splits. We have not yet gone onto the cross validation part of it. So if I'm doing a 80-20 split, actually 75-25 split in this case. So I have my 100 points, 75 used for training, 25 used for testing. And I just keep rotating my test points in this way or on the other way, it doesn't matter. This will ensure that each test point has been used exactly once during testing. This will also ensure that each train point has been used exactly how many times? In this case 3 times for 4-fold cross validation. Otherwise, for k-fold cross validation, each point in the test set has been used exactly once, and each point in the train set has been used in k-1 models.
Are these 4 different models or the same?
Okay, good.
Because you mentioned that we should not see the test data while training.
We have not seen the test data.
But in the second case, we already saw it when we trained the first.
Okay, so Kishan's question is that first, are these, so if you learn a model on each of the fold, are these different models or the same model? Firstly, they'll all be different models, and in each of them, you will always assume that the training and testing are kept separate. So there is no leakage. But then you get the question that what is your overall model? You don't have a single model now, right? In the train test split, you train on the training data, you test on the testing, you add a single model. But now you have 4 different models. What do you do about that? Sorry? Most accurate model, you are again going down that rabbit hole of where the students are trying to, this happens in practice. People will again pick up the best performing fold, and students I've also seen, not just, I necessarily don't mean students, I've seen people make this mistake of they'll choose the number k, how many folds to do based on what they get as the maximum best result. So again, we'll not do that. We'll pick up the fixed k before we start the experiments, and we report the metrics on the baseline methods as well as ours. But we have 4 different models. What do we do? You can report the mean and the standard deviation across the metrics for each of the fold, or just report all of them. But what is the final model? Do you take the mean of the model? Can you take the mean of the prediction coming from the model? You can do that, which becomes something known as ensemble learning or ensemble learning, which is the topic for the next lecture. How do you combine various classifiers or regressors?
But what if our this is discrete? So and we are taking these, we are doing it this way. First two, and we are putting yes as 1 and no as 0, and then if we are taking an average and we are getting somewhere 0.5. So what do we do that? For that?
So Deep's question is that, let's say we are talking about a classification problem. You have 4 folds, and so you have learned 4 different models, and now you will use these 4 different models in an evaluation setup, which is now a new test setup. It's none of the data that you've seen here. You make a prediction, you get 2 yeses, 2 nos, or 2 pluses, 2 negatives. What is your final output? Arbitrarily break the tie. In better methods of reporting errors, you will actually tell that I'm confused, I don't know. But typically methods the simple answer is that you'll either arbitrarily break the tie, or you'll just pick up the first one or do something like that. Typically people do that in ensemble learning. You take odd cases, but that's when you're dealing with 2 class problems. If you have 3 class problems, you'll have some difficulties there also. Okay, how do we do k-fold cross validation? Let's see that in code. This is the way you can from scratch write this code. This used to be one of the questions I give in the assignments earlier on. You split based on the size of the fold, and then you have to do some smart NumPy indexing. And then for each of the fold, you'll get the accuracy or the performance on the test set, right? So you can see that for each I in 1 through k, or in 0 through k minus 1, I have a separate train set and a test set. I train my model on the training set with the training labels. I make the prediction on the test set. I store all of them, I compute the accuracies. Or I could have used something known as k-fold method from sklearn. You train on, you do the split of the data set using this k-fold object, and then the remaining part is exactly the same. Now we come on to the next method, which is when we want to optimize our hyperparameters. Thus far we have not optimized any hyperparameters. Our hyperparameters, let's assume it's, for simplicity, is only the depth of the tree. So I then use a subset of my training data called the validation data, where I test the performance of my model. I will never use test set to optimize my hyperparameters. I think you should just memorize this, write this in front of your notebook, just never forget this line. This is also one of the biggest mistakes I've seen a lot of people make, including some top papers. They'll optimize their hyperparameters on the test set. So I've shown you 2 or 3 hyperparameters, one being the model depth, one being the, let's say, various parts of trees. There is yet another hyperparameter which I've unfortunately seen being used at times. What could that be? The random seed. So typically, if at the start of the experiment, you specify the random seed. I've seen that people have chosen certain random seeds, and there's a very funny paper on that also, that choose this specific seed to get the best results overall. But we'll not talk about random seed for now. Let's assume the model depth is the only hyperparameter of concern at this point. So we train a model. Now we will not train a single model, we'll train multiple models, because we want to choose which depth is the best. So on the training data, we'll train a model of depth 1, 2, 3, and so on. On the validation data, which is a part of the training data, so it's known to us, therefore we can validate the performance. We look at the accuracies which I get for each of the model, and then I pick up the one which gives me the best accuracy. And then I use that learnt model to make predictions on the test data set, and then I can compute the error metric. That's one workflow. The other workflow is find out the best the best depth or the hyperparameter which maximizes performance, and then on that hyperparameter train on the train plus validation data again. Right? 2 variants. First one just trained on the train data with different hyperparameters. On the validation data, you looked at the performance, you chose the one with the best performance. Now you use the model which was trained only on the train data, and then use it to make a prediction on the test data. The second one is slightly different. You figure out the best hyperparameter. With that best hyperparameter, train again on train plus validation, so that you can capture more data and then test on the test data. Questions on this? So I think we can probably take 4 or 5 minutes more and we'll finish. Otherwise, we'll have to start again the next lecture. So the way we write the code for this is you split your data set, originally data set x and y into train and test. Now you split again your train data set into training and validation. Yes. So I'm using the same methods. Train your original data set x and y using train test split, then train your train data set into sorry, we call that train and val data set. We split that again into training and validation. So thus far we will then have these ranges of hyperparameters. We will say the max depth we want to vary between 1 and 10, min sample split between 2 and 8, and criteria values is a discrete choice between gene index and entropy. So I put nested for loops, max depth in this, samples in this, criterion in this. With this I get one combination out of these 10 into 8 into 2, right? And I then fit my model on that. I store these results in a dictionary. Okay, I'll just show you the output. I store these results in a dictionary, and I then create a pandas data frame out of it, which looks like this. I can after that just figure out in this data frame what is the highest accuracy by sorting in reverse, and then choose that specific set of hyperparameters. Right? In this case 6, 5 and gene index, which gives the maximum validation accuracy. So it's something specific into number of, so I leave this up to you to study from the sklearn documentation. So if you just look at sklearn documentation, it's one of the criteria. Another cool small thing to show, I had here written nested for loops. I had 3 hyperparameters, so 3 nested for loops. I could have also used something known as itertools.product, and I can just call product of hyperparameters of this and this and this and this, so on and so forth, and then I'll get the overall. So I don't have to write nested for loops this way. Which brings me to now the last method. What is the drawback in this? In this current diagram, there is still only one train test split. Can you put a k fold on top of this? Right. So then the diagram would look like this. You divide your training data into k equal parts, where this is known as the outer loop, and in the inner loop you will do the nested cross validation. So this, let's look at nested cross validation in the next class, but you'd have to definitely revise till this point, otherwise this will just look like some unknown language to you. Nested cross validation is a slightly complicated concept. I can show the code for it. So this is a highly optimized code that I've written.